right. Good morning, everyone. We're gonna get started. Welcome to the AstroAI seminar. Today it's my pleasure to introduce Raza from McGill University. He told me this morning he just defended his PhD thesis, so it's fresh from it. And he was working with the group of Daryl Haggard, who's an old friend of us here as well. Today, Nair is gonna be telling us about gravitational wave events and how to use machine learning to better classify events and decide on which objects to follow up using a machine learning algorithm. I encourage everyone to interact with questions. We want open discussion. Other than that, Nair, the floor is yours. Thank you very much.
Thank you very much. Thank you for having me and for the opportunity to present and share some of the work that I've done throughout my PhD.
I think people at the back don't see very well the lower part of the screen. So if you have something important down there, then make sure to mention
it. Okay. Yeah. No worries. So I am particularly happy about making this sort of joke. I was like, do I do it or not? And then I was like, I'm never gonna have the opportunity again. So as of last week, I'm no more a candidate, but a PhD, which also means I'm on the thank you. It also means I'm going to be on the job market very soon, which is part of why I'm here. So if you want to talk about potential postdoc opportunities, I am very, very happy to chat about those. But yes, so today I'm going to talk about the work I've done on this machine learning model that we've developed for classifying candidate gravitational wave events detected by LIGO-Virgo. And this is work done in collaboration with the GWSkyNet team and my supervisors, Daryl Haggard at McGill and the Detroit Space Institute at McGill. So just to give everyone a quick background, gravitational wave astronomy really took off in 2015 when the two LIGO Hanford and Livingston detectors saw the in-spiral and merger of two roughly 30 solar mass black holes. And since then, in that last decade, we've not only seen mergers of binary black holes, but very excitingly, mergers of neutron stars and black holes, and also binary neutron stars. And these binary neutron star mergers are really, really exciting because they're not only producing gravitational waves, but also electromagnetic counterparts. So we've seen kilonovae, we've seen gamma ray bursts, and in fact, we've seen this for only one event confirmed so far, GW170817, which gave us a host of information, really rich data sets. We're able to find out, synthesis of heavy elements through our process. We're able to constrain the neutron star's structure equation of state through tidal deformability, and even get independent measures of a Hubble expansion rate. So these are really, really exciting events that we really want to follow up on. And it's an exciting time to be doing gravitational wave follow-up because the LBK, well, they just wrapped up their fourth observing run less than a month ago. And there have been more than 250 significant candidate events. Compare that to 90 events that we saw in 01 to 03. We see that with each observing run, the detectors get more sensitive and there's more events detected. And in particular, I'm going to highlight this one event, S240422ED, which was a candidate event that happened in April of last year. So this was a really promising candidate neutron star black hole merger. And there was a lot of interest in follow-up. In fact, in the 1 month after this alert went out, there were more than 90 GCN circulars sent out. So dozens and dozens of teams pointing their telescopes wherever they have, triggering their targeted opportunities, and trying to see if there was a counterpart. Now, this all is made possible by the LBK releasing public alerts for follow-up observations. So these are rapid, on the order of 30 seconds or so after an event is detected. And the main thing that's released is localization information for pointing telescopes. But before astronomers can decide to follow up this event, we have to decide whether the event was actually even real or not. And in fact, if we look at the events alerts that were sent out in 03, which was a previous LDK observing run, on the order of about 40% of those turned out to be glitches. Yes.
Sorry. So the localization is not very well determined by the gravitational wave signal itself, correct?
It
Is? Oh, waiting, what's the typical error of the?
really varies depending on how many detectors were online and observing
Okay.
at a given time. So if it's one detector, it's basically the whole sky or half the sky. You know, it's typically 10,000 square degrees.
Alright.
But something like this is a very typical shape for a two detector event. So this was a Hanford and Livingston detector.
So that's with two detectors.
Yes, this is with two detectors. So with two detectors, you can see 90% localization area, about 1,000 square degrees.
Still pretty large area.
Still a pretty large
I
area.
guess my question really is, do you need the electromagnetic counterpart of any sort in order to follow up with other telescopes? Do you need at least one electromagnetic signature?
It depends on how good your localization is. But from gravitational wave data alone, for most targeted follow-up, yes, you need some counterpart. You can have things like Rubin, very large field of view, but even that is 10 square degrees, right? So getting an electromagnetic counterpart really helps to play things down. Yes. Sorry, can you say that again?
Alerts will allow in 30 seconds.
30 seconds. Yeah, typically.
That's fine, and then we'll sort of determine because the positive.
No, so that's one of the key drivers for what I'm about to get to next, which is the model we worked on. So the LVK pipelines, they try to do a quick analysis of what the source might be. And then the aim is to get those alerts out as fast as possible. And at the same time, they trigger, more dedicated, longer follow-up analysis as well. But that can take like hours to days. So there's two things happening on two different timescales. But these are the first alerts that are sent out as fast as possible to the community so that you can try to, trigger whatever programs that you might have. So the alerts can be false alarms. There's a lot of sources. LIGO detectors are very, very sensitive. So there's lots of sources that can mimic gravitational waves, but are actually terrestrial in origin. And even if the source is astrophysical, we want to know, does it likely have an electromagnetic counterpart? Because for run-of-the-mill typical binary black hole mergers, we don't expect any counterpart. We want to have a neutron star black hole source or a binary neutron star. And so you can ask, S240422ED, the really interesting event, was it really an NSPH merger or not? And I'll leave that as a cliffhanger for now. So that's where, yes.
Yeah. When you say glitch, you're talking about those sort of non-gravitational wave, but what would you expect from terrestrial or is this literally instrument glitch?
It's terrestrial sources. Yeah, we use it as a generic name for any excess power that we see, any transient excess power that we see in the detectors. Yeah. So some of those we know what the sources might be, like there's light scattering within the optics that can sometimes produce glitches, but some of them we don't know what the sources are, and those are more nefarious ones. Yeah. So that's where the GWSkyNet algorithm comes in. So this is a neural network based model that's designed to do real-time classifications of LIGO-Virgo candidate events. And the interesting part is that GWSkyNet and GWSkyNet-Multi, they only use information that's released in the LDK public alerts. So information that's publicly accessible to all. So that includes sky localization maps that we were just talking about. So the typical, probability region that you see over here. But you also get a full 3D probability. So we also use projections in these 3D volumes. We have things like estimates for the distance and a few other metadata in terms of what the signal, how loud the signal is, how coherent it is across detectors, and which detectors we're on. And so this was first developed as GWSkyNet, which is a binary classifier telling you whether the source is a glitch or astrophysical. This was in work led by McGill at the University of British Columbia. And then was updated in work led by Mervyn Chan for the O4 observing run. And in fact, the GWSkyNet pipeline is now integrated within the LGK. And so you get GWSkyNet classifications directly from you. Importantly for my work, this was then further developed into a multi-class classifier that now, along with having a glitch versus all binary model, it's a series of 3 one versus all models. So you have a glitch classifier, a neutron star classifier, and a binary black hole. And so just a few more details about the model itself. So this is based on simulated binary mergers that we have for the neutron stars and black holes. And we had about 1,000 glitches from the first 2 observing runs that the model is trained on. And as I was just mentioning, the inputs are based on just the sky localization information that's released in the public alerts with this base star pipeline from the LBK. And we get a classifier score between 0 and 1 for all 3 classifiers, and then we implement them in a hierarchical manner to get a final classification. And we saw, yeah.
Sorry, so the input is, when you say the sky map image, you mean the localization map, something like
Yes.
that?
This is exactly what the inputs are.
Oh,
So there's
okay.
1 image for this, 3 images here. We have inputs for the distance and uncertainty of the
So
distance.
the signal itself of the detector is not part of the input, like
No,
the
no.
strain? Okay, okay.
So the strain information is not released publicly.
Oh, I see. Okay.
Yeah. So the whole idea is to have these inputs that are accessible. You know exactly what's going on, what's going into the model, and only using localization information.
Could you explain what those things are down on there?
These 3. So these are so the base star algorithm gives you a 3D probability localization. And so you did different projections. So this is the right ascension declination, right? Polar angles. This is just the X, Y, Y, Z, and ZX projections. Yeah. So of this banana shape. Yeah. Was there another question? Okay.
It was also about, I guess most of the information on whether it's what type of merger it is like in the wavefronts of the signal, right? But you answered it already, it's not yet available, so
Yeah,
a rapid follow-up, we want to have like the data that's available.
exactly. That and, that is, if you have the raw data stream, you will have the most amount of information there. But even then, this is a challenging task, right? Like in O3, even when running, the pipelines, the internal LDK pipelines on the data coming in, there was a very high false alarm rate. So this is a challenging task, even if you have access to the raw data. But yes, in this case, we wanted to have public alert data because that's what's immediately available.
How long does it take to process the raw data and get like the frequency of time,
Spectrograms?
the spectrograms?
So those are only released by the LBK after full analysis of the whole data observing runs done, or parts of observing runs. But that's typically a year or 2 after the events happen. Yeah.
Too late for follow.
Yes, yes. For most follow-up, yeah. That said, the LVK do provide some follow-up on the order of hours to days. If they do refined analysis, those updates can come through. But that's still only, refined sky localization maps, things like that. Raw strain data, information about, masses of the source, spins of the source. Those only come out in the final catalogs, which is on the order of a year or so. Okay, so with GWSkyNet-Multi, the model is working well. It has high accuracy in the test set when we tested on O3 data. But one of the big things that was a driver for why I joined the team and to work on it was we really don't know how the model is working and how it's making the predictions that it's making. It's a convolutional neural network, many layers, many different branches, all coming together. And in machine learning, especially with neural networks, they're notoriously known to be black boxes. And so we wanted to know, what is it learning? What is it looking at? And what are the important inputs that are driving the classifications? And so just to give an overview of the rest of this talk. So I'm going to first talk about the work we did in trying to explain the model and its predictions, try to sort of uncover the black box. Then I'm going to talk about how we use some of the insights we learned to develop a updated, more robust model for the fourth observing run that just finished. And then finally, a little bit about trying to push the model limits to try to classify inherently ambiguous events that are in the lower mass cap, and where that led us in terms of further insights to the model. So just as a schematic to motivate our explainability studies, here we have just a very rough sketch of how human understandability of these models decrease as they get more and more complex. But at the same time, these more complex models have been shown to be much more powerful as well. So you have, deep learning model methods like GWSkyNet-Multi on this part of the spectrum where they're highly uninterpretable. And so what we tried to do is use post-hoc explainability methods to try to increase our understanding of these models. And the idea is to compare them to how we, as physics experts, understand the systems that they're applied to and increase our trust in their validity. And so our approach to doing the explainability studies was a simple one, but very powerful. It was through perturbation studies. And so the idea is simply we take all our inputs and we perturb them in understandable, intuitive ways. And so, for example, one of the things is you look at the sky localization area of the map that you're looking at. So this is the same map that you were seeing before, now it's just projected onto a 2D grid. And you say, okay, what if the sky localization was much worse? What if maybe the source wasn't as loud, it was too far away, whatever, that produced a sky localization area that was 4 times as large? Or the other way around, what if the localization area was much better? How would that impact what the model is outputting and thus what it's learning? And we do this for all the inputs. We try many, many different types of perturbations with images, with the other values that we have. And we do this for each of the models. So we have 3 1 versus all for glitch, neutron star, and black holes. And we then try to summarize these effects over the whole population that we study. And so I'm just going to go through a couple of these. So as an example, here is what we saw when we perturbed the distances. So you have on the x-axis how much the distance is being scaled, and on the y-axis how the score on average changes across the population. And so for this, we have the glitch classifier in blue, the neutron star in orange, and the binary black hole in green. And so we see that at smaller distances, the neutron star's score increases, which means that these sources are more likely to be classified as neutron star bearing sources. Whereas the score decreases at smaller distances for the binary black hole classifier. So smaller distances, much more likely to be classified as a neutron star, larger distances, much more likely to be classified as a binary black hole, which is consistent with our understanding of these sources, right? gravitational waves, the amplitude of the signal depends on the masses. And so binary black hole mergers are more massive or can be more massive than neutron star mergers. So they're detectable to much further distances. Yeah.
You might have said this already, but what exactly are you referring to with the glitch?
Oh, so glitches are transient instrumental noise in the detectors.
Okay.
Yeah. These are not like pulsar glitches or anything.
Right,
Yeah.
yeah.
The nomenclature is, I guess, can be confusing. But this is noise, basically, transient noise.
Sorry, can I interrupt with
Yeah.
a high level question? So far my understanding is that the classification is based mostly just on positional information plus some sort of scaling for the distance. Sort of. So there's no information about the signal itself.
No,
I guess you'll say this, but how is it able to classify whether, is this based on some sort of prior or where along the galactic plane you expect things to happen? Or is this based on some prior on where the populations of progenitors can be, or is,
no.
okay,
It's not. It's only looking at that localization information that I showed before.
Okay.
This. So this is literally all the information they're putting into the model. These images and then these this metadata. So there's no priors. We don't tell it, where the galactic doesn't know where the galactic plane is. Doesn't know what binary black hole sources are. None of that.
Regarding that question, so in your simulation, you must have some sort of distribution when.
Yes. Yes.
So you already may have a different distribution for neutron star mergers versus black hole mergers, so
Yeah.
that may get into the play in terms of your testing.
Absolutely, yes. So in that sense, yes. When we simulate our mergers, we don't typically expect to see binary neutron star mergers beyond some horizon scale. That's typically 200 megaparsecs or so. But for binary black hole mergers, you see them up to a few gigaparsecs. So that is where this comes into play. However, that information only shows up, maybe in the distance parameter over here. So we simulate the mergers, we inject it into LIGO-Virgo detector noise, we simulate recovering those signals and then producing these rapid sky localizations. And it's only these final products that we then train the model on. So it explicitly doesn't know about any of this, distributions or population modeling or anything. There was
How does that then, how are you then distributing those over the sky? Is that actually uniform distribution?
It is uniform, yeah. So it's isotropic, uniform. We don't take into account, a galactic plane or anything. Yeah. Okay. We were here. Yes, okay. So we saw dependence on smaller distances, neutron stars, larger distances, binary black holes. And we see a minimal effect for the glitch classifier, which is also consistent with our understanding, right? These glitches are not physical, astrophysical events. And so there is no real distance dependence for these transients, these terrestrial transients that are happening in the detectors. And so the takeaway we have over here is that the distance input is being used as a strong discriminator between neutron star bearing sources and binary black hole sources. And so we do the same for all the other inputs. And what we find is that in addition to the distance, it's the sky localization area and the coherence factor that's really driving the glitch classifications. So we see that for larger sky localization areas, the model is much more likely to predict these sources as glitches. And similarly, for smaller coherence factors, they're much more likely to be classified as glitches. And these two things are interrelated, right? The less coherent the signal is across multiple detectors, the more likely it is that it is some chance coincidence of excess noise in the two detectors. Whereas for astrophysical sources, you would expect them to be much more coherent across multiple detectors. And that also drives, how certain you are where the source is on the sky. So with glitches, you are usually less certain. The sky localization is worse. And that can also help us understand some of the misclassifications that the model is making. So here we have the event S190425 or GW190425, which GWSkyNet-Multi predicted to be likely a glitch, so not astrophysical. However, the LVK confirmed in their final catalog that this was in fact a binary neutron star merger event. And so for this, we can see that this huge sky localization for this event is what's driving GWSkyNet-Multi to misclassify the event as a glitch. So we can identify some biases in the model this way as well. And we can do this more systematically for all the different events that we had in 03. So here what you're seeing is on the x-axis, the true classifications that we have from the LVK final catalog. And on the y-axis, these sources distributed according to some of the inputs that the model gets. So in this case, it's the distance to the source. And each of the symbols tell you what the source is classified as by our model. And so these binary black hole sources, all of these are correctly predicted as binary black hole sources. But these are misclassified. Some of them are misclassified as glitches, some of them as neutron star sources. And so you see that all three sources that are misclassified as neutron stars are separate from this distribution over here because they're at much smaller distances than what the model has learned to expect for neutron star sources, for binary black hole sources. And we do the same thing for the sky localization area. And again, we see that the sources that are misclassified stand out. These sources that are actually astrophysical events that are misclassified as glitches by the model all have very high sky localization areas. And so to wrap up that study, what we find is that the model is focusing on three main things. That's the sky localization area and the coherence factor for deciding between real sources and glitches, and the distance input as a discriminator between sources that have neutron stars and binary black hole mergers. And through our perturbation studies, the trends that we identify, they can help explain the misclassifications that the model is making and identify where it's being biased and where it's limited. And importantly, this type of study shows that it's important to have explainability or interpretability at some level when we're developing machine learning models, as they give us insights to how much, in which domains and which regions we can trust that the model is making a correct prediction. And so we can more reliably use these models. And so that led us to the question, how can we use these insights to build a better model, more robust model for the 04 observing run? And so the idea is to use these insights and develop a updated GWSkyNet-Multi, very inspired name, we call it GWSkyNet-Multi II now, and see, okay, how can we build this, make this more interpretable and simpler? And so one of the things that we did was, after we realized that what the model was looking at is mainly the sky localization area, we can take a whole complicated input like an image with 16,000 pixels in this case, and synthesize it to a value that we understand. So we said, okay, we can just input the 90% sky localization area to the model. And that's something that we have a much better physical understanding of. It's what part of the sky that do we have to cover to have a chance of observing the source. And we updated the training data set as well. I'm not going to go too into that. We use updated simulations, latest examples of glitches from the third observing run. And importantly, we completely overhauled the model architecture. So this is what we had before. We had images for the sky maps and volumes, convolutional branches, everything coming together. And these are all the changes we've made. And what this led us to is a much simpler, much leaner model. So this is what the model looks like now. This is in its whole entirety. So I'm just going to go step by step for each of these layers. So this is now 7 inputs. There's no more images. It's all numerical values. So it's tabular data. And what this means is that not only is the processing much faster, you don't have to do reprojections of the 3D localizations and whatnot. But it also is more interpretable to us. So Rafael was asking about, when we look at the shapes, what is going on in these kind of localization maps. It turns out it's also difficult for even experts to ascertain what exactly does this particular shape versus that particular shape mean. Whereas if you know the localization area, that's much more understandable, and we have intuition for that. We also have a factor of 60 less trainable parameters in terms of the model. And that's because this is very, very simple now. It's just 2 layers of 8 neurons each. In fact, this is so simple that when we submitted the paper, the referee said that this is should not be classified as a deep learning model. To which we removed the deep learning part. So this is a neural network model officially. But this really shows us that sometimes we over-apply, overcomplicate our models when there really is no need. And finally, for some of you who are more familiar with machine learning methods, now that the inputs are all tabular, you might be wondering, why do we even need neural networks? What about other architectures? And we did try other architectures. So for example, we tried using XGBoost. And what we found was that the neural network was still performing better, and it seemed to be able to generalize better for events that it didn't see in its training data set. And finally, but importantly, we have that this is now a single model that's multi-class, and it produces fully normalized probabilities for each of the classifications. And we were also able to separate the neutron star branch into neutron star black hole merger or binary neutron star. So now you have classifications that are fully consistent with all possible source types that we get from the LBK. And so coming back to the original cliffhanger that I left you at, what about this interesting potential neutron star black hole candidate event that happened in April of last year? So the LBK initial alert was for a neutron star black hole merger. GWSkyNet-Multi, the original model, actually supported that classification. It said that this is a neutron star bearing source. However, the updated model predicts that this is most likely a glitch instead, with a 58% probability. And in fact, after further analysis by the LBK, the event was reduced to likely being a glitch. But this happened, a couple of weeks after the initial alert was sent out. So all of the follow-up observations that were made, the 90 GCN circulars that were sent out, GWSkyNet-Multi shows that this source was not worth following up.
Did they detect anything?
Nope. So there was no detection either. So this shows you, there's a lot of resources that can be saved by having an alternate pipeline that can give you an estimate of whether the source is even worth following up or not. That said, GWSkyNet-Multi is not perfect. It does not capture all of the glitches that are sent out. So here is a confusion matrix showing what we have, the GWSkyNet-Multi predictions on the x-axis, and what the LBK updated classifications are on the y-axis. And this is for events in O4A and O4B, and I'll just say that this is a preliminary comparison because we don't have all the final catalogs out yet. We have the O4A catalog out now, but not O4A and O4B or O4C. And so we see over here that in O4A and O4B, there were 21 events that are likely glitches for which alerts were sent out. And GWSkyNet-Multi was able to detect 14 of those, so about 2/3 as glitches. There are still these 7 events that GWSkyNet-Multi also incorrectly classified as probably astrophysical. So there is still room for improvement in reducing these false alarms. Overall, however, the updated models predictions are consistent with the LVK's updated classes for 93% of events. So it's still in a very high performance regime. These predictions are now also being made live and updated on our webpage. So we do this with a latency of less than a minute. So someone was asking about 30 seconds from the LVK from detection until alert. Another minute or so until this becomes available. But if you're worried about seconds or tens of seconds, the model is also available to implement in your own follow-up pipelines. So from start to finish, it takes about typically 10 seconds on my Mac to run. So you can access the Git or the predictions page over here. And then I also wanted to highlight another recent event. So this actually happened in August this year. This was a really interesting event. Also, a lot of interest in following up because this was a potential binary neutron star merger. So the LVK gave a probability of about 30% of it being a binary neutron star, but 70% that it's a glitch. And the reason why a lot of folks got interested was because a potential counterpart was seen with this Wiki transient facility. Now, this potential counterpart remains highly debated. I don't know if some of you might have been involved in following up or are aware, but there was follow-up by Pan-STARRS, and that team predicted this is most likely a type 2b supernova instead of a kilonova. However, there are still other teams that say that this might be a kilonova, just not a typical one that we might have seen with GW17 or 817. However, the point being over here that with GWSkyNet-Multi II, we have a much more confident classification that this is a glitch. So if you weren't sure just based on the LVK classification, our model says that this is also likely to be a glitch. And so it gives you an alternate source of info for making these follow-up decisions. We still don't know what this is until the final LVK catalogs come out. But so far, I would say there has been no confirmed counterpart detection. So summarizing the GWSkyNet-Multi II paper, we've significantly simplified the model, made it more interpretable, while it still has a very high classification accuracies. And it now provides a fully consistent classification scheme. So whether the source is a glitch, binary black hole merger, binary neutron star, or neutron star black hole. And these classifications are being made publicly available in near real time. So you can access them right away, use them to trigger your follow-up observations if you want or not. And so that brings us to the final part, which is, can we extend this model to identify inherently ambiguous events? So we've had a historical lack of observations of black holes in this interesting regime that's between about 2 to 5 solar masses. So this is a schematic that's showing you in orange observations of compact objects in electromagnetic sources. and in blue, observations of compact objects and gravitational waves. And this observational bias has led to a lot of interesting theories and considerations for what's going on in this regime where we don't see black holes. And this was spurred, there's been recent interest in this, what's called the lower mass gap, because there was a gravitational wave event detected that is very likely spanning this range. And so we know that this mass gap is actually not a gap, it's not completely empty. And so this transition region between neutron stars and black holes, that becomes difficult to classify and see what's going on. And on top of that, we also have uncertainty in the boundary between what's the most massive neutron star that you can get. So whether it's 2.5 solar masses, 2.2, 3 solar masses, that also remains uncertain. And so our idea was to try to train the model to specifically target these types of events and give a probability for whether the event was in the mass gap or not, or probability that has a neutron star. And so this is showing you how we assign those probabilities. So we did 20,000 simulations of merger events using an astrophysically robust data set, latest population modeling that we have, latest detector characterizations that we have. And so over here, you're seeing each of these dots represents one merger that we have in our simulation. And they're distributed according to the masses of the binary. So you have mass of the primary on the x-axis, mass of the secondary on the y-axis. And the color denotes the probability that the source belongs to the mass gap. So this over here, roughly between 2 to 5 solar masses, more likely to be classified in the mass gap, and otherwise not. And for the neutron star sources, the boundary is much sharper. But you see over here, these events are, binary neutron star mergers or neutron star mergers involving a neutron star that would be electromagnetically bright, whereas these ones over here are binary black hole mergers. And so we train the model to try to predict these probabilities. And the kicker is that it didn't work as well as we wanted to. We tried many different architectures. We tried a whole bunch of hyperparameter tuning, different weightings, everything that we could think of, different inputs. And this is the best that we came up with. So what we see is if we plot the true event probability on the x-axis and what the model is predicting on the y-axis, each of this dot is showing you the results from a test set. And if this was a perfectly accurate predictor, everything would lie along the diagonal. And that would be the best case scenario. Whereas for us, what we found was we binned each of these predictions according to the true event probability, but that's to see what trends might come up. And what we see is that for low probability events, so events that are, binary black hole mergers, that are not in the mass gap, those are identified well by the model. But as soon as there's a marginal probability, this source is in the mass gap or has a neutron star, the model finds it difficult to distinguish these sources. So there's basically very little dependence within this very narrow regime of mass gap and neutron star sources. And so we wanted to investigate why this was happening. Why is the model really unable to identify these sources? And to do that, we looked at the chirp masses for the source. So this is the only equation I'll show you today. It's just the chirp mass is just a combination of the two binary parameter masses in this specific combination. But it's important because for gravitational wave analysis, it's the quantity that determines the leading order, both the amplitude of the signal and its frequency evolution. And it's a very well measured quantity by the LBK detectors. And so what we found was that when we looked at how the predictions vary with the chirp mass that we have known from our simulations, there's a strong correlation between the predictions and the chirp masses. So for example, if you look at the panel on the right, this is showing you the chirp mass on the x-axis versus what the predicted neutron star probability is from the model. Again, each of these dots represents one event in our test set. And overlaid are binned mean values that we have that are for the true distribution of neutron star probabilities versus what we predict in the pink. So the key takeaway here is that these two distributions, these two curves, model each other, follow each other very, very closely. And so the model is picking up on the chirp mass dependence for these sources. We see something similar when we look at the mass gap predictions, but it's not quite as tight. There is a dependence on this chirp mass quantity that's much more apparent at higher chirp masses than at lower chirp masses. And then we tried to compare this to actual events that we have from the O4A catalog that very recently came out. And so we're seeing what we plotted is the same thing, but now these are the measured chirp masses from O4A events from LDK. So you have the predicted mass gap probability in green and the predicted neutron star probability in orange. And we see similar trends that we saw before. The model is able to correctly identify sources that are not neutron star bearing sources, not mass gap sources, for merger events that have chirp masses of more than about 15 solar masses. These are some known outliers. We can talk about them if you're interested, but for now we can ignore these. But then this interesting regime over here, we find that the chirp mass information is not enough to uniquely determine what the source is. And so for that, we would also need to know the mass ratio of sources. So this regime over here, where the model is making marginal predictions, this is where it starts to get murky. And so the key takeaways from this, this final project is that the boundary between neutron stars and black holes, it remains difficult to distinguish. Even with our machine learning model that was working very well in distinguishing real events from glitches and black holes from binary black hole mergers from other merger sources, this very narrow regime still is difficult. And we find that the model is able to infer chirp mass information for making these predictions, but not the mass ratio, which is a key additional step that we would need to really classify the sources very, very accurately. However, looking forward, this also points to the possibility of building a model that explicitly can predict the chirp mass. So now that we know that the model can infer some sort of information about this, can we directly provide the chirp mass as an output to the community? And that'll be really helpful as, we started to see that this mass gap is not actually empty. We are observing more and more events in this regime. And so having that information on hand right away would be really useful for modeling and for follow-up in future observing rounds. And so I'll just summarize and end over here. So GWSkyNet-Multi is this neural network-based machine learning classifier that we developed for candidate gravitational wave sources for doing rapid follow-up. And we did explainability studies to show that the model is learning dependence on sky localization areas, the distances, and the coherence factor for the event. And these things, these inputs, while they drive the current models, they also led to insights that we were able to use to build a more robust, more interpretable, a simpler model, GWSkyNet-Multi II, with predictions that are now available to the public in real time. And finally, the events that we saw near the neutron star black hole boundary, they still remain difficult to distinguish in this rapid analysis. But it's exciting that the model is able to learn chirp mass information that we could potentially predict in the future. So with that, I will end. Thank you.
Thank you, Nair, for a very nice talk. Question in the back.
Hey, great talk, thanks for that. Going from SkyNet-Multi II to instead of the statistical from
The accuracy that we had from on GWSkyNet-Multi, 90% was on the test set. On the O3 events, it was 80%.
Okay.
Yeah.
So in the O3, it was 80 to 93, is that correct?
Mhm.
Okay. Yeah, so I was wondering, like, so I'm presuming the development of SkyNet-Multi II was an iterative process.
Mhm.
You tried architecture and corporate governments. So if you do that repeatedly, isn't there like in fact that you're overfitting the new test set? So how do you ensure that it's not an overfit? 93 is not an overestimation.
Yeah. So the 93% number that comes in is the consistency that we have with O4 alerts. So all of the training and all of the in-house testing that we did was based on simulated mergers. So that was what we tried to optimize. So because, from LBK, we only have, on the order of 100 or so events. We trained on thousands and thousands of simulated mergers and glitch examples from O3. And that's what we tried to optimize in our architecture.
And that's
And-
separate validation.
Yes, yeah, that's all separate. We don't even think about, we don't even touch the O4 alerts. And then the 93% number comes from this, where now that the model is finalized, we're just making predictions. So this is showing you consistency for the predictions that after we finalize the model. So it's a great question because we struggled with this. We were like, should we train on maybe O4A or validate against O4A data and try to optimize that before we deploy it? And then it ultimately came up to be a philosophical decision as well of if the model is designed to predict on these O4 events, we don't want to overfit it. So these are all predictions. This is nothing that the model has seen before. But as I said, these are preliminary comparisons. So once the final catalogs for all of O4 are out, then we'll have an actual analysis of how accurate the model ended up being.
Thanks. Yeah.
Am I understanding right? You are not using mass information that LBK announces, right?
Yep, we're not.
So I can understand why you are not using that, and I can estimate, but in terms of classifying the glitch, wouldn't that be very useful? Because there looks like a glitch will be quite different pattern in terms of SkyNet versus the mass. So that may be very useful to just get rid of or identify the glitch first. Wouldn't that be the case?
You're saying using the masses to identify glitches?
Yeah, mass information, that's publicly available, right?
So mass information is not publicly available in real time.
Oh, okay.
Until June of this year. So as of June of this year, in O4C, so last few months of O4C, LIGO started releasing what they call coarse bin chirp masses. So they give you a probability that the chirp mass might belong in, let's say, between 1 to 2 solar masses, or 2 to 5 or something like that.
Okay.
Yeah. So when we were developing GWSkyNet-Multi and updated works, up until then, there was zero mass information available. So we didn't, in all of the work I showed for here, we didn't take into account any mass information. That said, for distinguishing between astrophysical events and glitches, I'm not sure how the mass information could be used. Because when the mass information is released, it's based on the assumption that the source is astrophysical. So what the LBK say is that if we assume that the source is 100% astrophysical, then this would be its chirp mass, coarse bin chirp mass. for deciding between whether the source is a glitch or astrophysical in the first place, yeah, that would be difficult. It could be very useful, and it should be very useful for deciding between neutron star sources and binary black hole sources.
Okay.
Yeah, because the mass, the chirp mass does determine what the source could be in certain regimes. For the sky localization maps, I think you mentioned using those for distinguishing between astrophysical signals and glitches. Yeah, I mean, we use that for GWSkyNet-Multi. But as I showed, we found that in the sky localization maps, all the model was learning was the size of the localization, not necessarily any other information. And so we could just synthesize that ourselves to one number and input that to the model.
Yeah, so you are performing the simulation, right?
Mhm.
And then which kind of, because if you are building a glitch classifier, which kind of glitches are you accounting for?
All of them. So in the updated model, so for GWSkyNet-Multi, we use glitches that were identified by this glitch algorithm. I'm completely blanking on the name right now. It's another machine learning. It's a collaborative community machine learning project. Completely blanking on the name right now. But it was identified through there. So it was different types of glitches, scattered, flip glitches, Tomties. There's like 18 different classifications that we have for what that glitch could be. And for the updated model, what we used were events that were identified by the detection pipelines, but that were ultimately determined to be non-astrophysical.
So gravity spy.
Gravity spy, yes. Sorry, I was completely blanking. Yeah, so in the first model, it's glitches identified by gravity spy.
So I guess that the main advantage of all these methods are that they are faster, right? Because I don't think that you will expect the classification to be better than where you use.
Yes, exactly. So the two main reasons why the whole thing was developed is that, yes, you want to have something very, very fast because you want to point and start observing right away, right? These transients that we have, like the kilonova, they can have very quick rise times on the order of hours, peak half a day later. So you want to have analysis that's as quick as possible. And then the other thing is that, as I said, even with access to the raw data stream, you can detect sources that are not astrophysical and send out alerts. And the state of the field currently, because we've only had that one event, GW17 is that now we're desperate for a binary neutron star merger, a multi-messenger event. So the community's threshold for accepting false alarms has been increasing with every year that passes. So now, the LVK errs on the side of caution, more false alarms as opposed to potentially not releasing information about a binary neutron star merger. Unfortunately, we haven't observed any counterparts yet, but we're hopeful.
There's a question online.
Go for it.
Yeah.
If the glitch and signal from the merger events overlap, can the system identify the signal? Can the method separate the glitch from the signal and recover some property of the event if it overlaps?
Currently, no. That's an excellent question and something that we struggled with and debated about for a long time. And the reason we decided not to train on glitches overlapping with signal was because these events are ambiguous in nature, right? They don't have a singular label. Is it a glitch? Is it a neutron star source? An astrophysical source? We're not sure. That said, this does happen. LIGO sources have glitches and astrophysical signals overlapping. It's one of the things that we've highlighted as a potential next step in expanding the model is training on these inherently ambiguous cases that are both glitches and astrophysical signals.
All right. quick one maybe, or oops, Sudani.
Kinetic follow-up of additional events like guessing if you have a binary neutron star and neutron star, both means follow-up. So why does the model care about categorizing that?
Yeah, so both means follow-up, but the probabilities of follow-up are different. So even for a neutron star black hole source, those can potentially have a counterpart, but not in all cases. In fact, for most of those sources, we still expect no counterpart, because it depends on whether the neutron star is tidally disrupted by the black hole before the merger happens. And there's work, so Sylvia Miscavonu has done work on this, simulating neutron star black hole sources. And in her work, it's about 10% of the sources that are NSBH are expected to be electromagnetically bright. So in this sort of stratification for a binary neutron star, almost 100% probability that you would see a counterpart. NSBH sources, 10-ish% that you will see a counterpart. Binary black holes, 0. So it's still really important to distinguish NSBHs from BNSs in terms of the potential.
All right, well, we need to let people free for their
Yeah.
continue day. Nair is here today and tomorrow, sitting up in 412. If you want to talk to him or just send me an email, I can connect you. Thank you very much for a nice talk.
Thank you.